डियर स्टूडेंट्स, आज के लेक्चर का टॉपिक है वन वे स्लैब डिजाइन प्रॉब्लम। प्रॉब्लम स्टेटमेंट है एन ऑफिस बिल्डिंग हैज ए हॉल ऑफ साइज 3 मीटर by 9 मीटर। डिजाइन द स्लैब which resists a live load 3 kN per square meter. The slab rests on 300 mm thick walls. Take M20 concrete and Fe415 steel. To begin with the solution, I have just visualized a diagram for this room. The room is having a 3 meter shorter span, that is the width of the room, and the longer span, that is 9 meter length of the room. So for the slab over this room, its Lx is 3 meter and Ly is 9 meter. So if we see here, the span ratio Ly by Lx comes 9 by 3, that is 3, which is more than 2. So according to IS-456-2000, it is a one-way slab. Now to stepwise start the design process. So the first step is to determine effective depth D, that is from deflection control criteria. As per IS-456 page number 3738 and its figure 4, if we assume a steel percentage 0.6%, then from figure 4 we get a modification factor 1.15. So according to the IS code guidelines at page number 37, and this slab is resting on a wall, that is a simply supported slab. So a case of simply supported one-way slab, which is just like a case of simply supported beam, from deflection control criteria, the LYD ratio comes 20 into modification factor, and from this relation, the effective depth of the slab D comes L divided by 23, that is 20 into 1.15 is 23. So L is the shorter span, that is 3 meter. So in millimeter, 23,000 divided by 20, that is comes 130 millimeter. So we got the effective depth of the slab 130 millimeter. In addition, now we want to calculate the overall depth of the slab. So it is very important to understand here, in case of slab, what is the effective depth small d and capital depth, that is overall depth. So I would just like to explain that in case of one-way slab, there is an area of steel nearer to the bottom surface, that is the tension surface. If the area of this steel is, suppose, a diameter of 10 millimeter bar, then the distance from the top of the slab to the center level of the bar, that is the reinforcement, is the effective depth. Now below the bottom of the bar to the bottom of the slab, so we have a nominal cover. We generally take 20 millimeter in case of slab, nominal cover or say clear cover. So from the center of the bar to the bottom of the slab, so this comes the half the diameter of the bar, that is 10 by 2, plus the nominal or clear cover 25 millimeter. So 25 millimeter is its effective cover. So if we add the small d effective depth with the effective cover, we can get the overall depth. So we will calculate this in our next step. So we got capital D, that is the overall depth of the slab, small d plus effective cover, that is 130 plus 25, 155 millimeter. So we got the total depth of the slab. By knowing the total depth of the slab, now we can calculate the total load which the slab is supposed to resist. Because the slab is having its own RCC material, so its dead load is there. So dead load of the slab would be the total depth of the slab, capital D, in meter 0.155, into the 1 meter width of the slab. We generally take in case of one-way slab, that is, we design a one-way slab for 1 meter width, and from this concept 0.155 multiplied by 1 multiplied with the density of RCC 25 kilonewton per meter cube, we get 3.875 kilonewton per meter. Now the question has given the live load 3 kilonewton per square meter multiplied the width of the slab 1 meter, that is 3 kilonewton per meter. And in addition to this, we take extra floor finish load, that is the load of the tiles or the finishes on the slab surface, and this is generally taken 1 kilonewton per square meter multiplied with the width of the slab 1 meter, it is 1. So total actual load on slab comes 7.875 kilonewton per meter. Now as per IS code, we have to calculate the design load. So design load is the total actual load multiplied by a factor, that is the partial safety factor for load 1.5 is multiplied with this, and total design load comes 11.81 kilonewton per meter. Now the next step is calculation of effective span. So as per IS 456 page number 34, to calculate effective span for a simply supported beam case or a one-way slab case, we have two options. The first option is the clear span 3000 millimeter plus the effective depth small d. So 3000 plus 130 comes 3130 millimeter. And the second option is the center to center of the support. So as you have seen in this diagram, that the slab is having one support of 300 millimeter, the internal span, clear span 3 meter, another support 300 millimeter. So from center of this support to center of this support we have to calculate. So half 300 by 2 from this side plus 3 meter plus 300 by 2 millimeter from this side will give us center to center of support. So we get here 3000 plus 300 by 2, 300 by 2, that is 3300 millimeter. Now as per guidelines of IS 456, the smaller of the two values would be the effective span. So L, the effective span comes 3130 millimeter, that is the lesser of the two values. So this way we have got the effective span. Now the next step of this slab design, to calculate the bending moment. Now to calculate the bending moment, we have to correlate this one-way slab to a simply supported beam, and a beam loaded with a UDL, that is 11.89 kilonewton per meter for a span of 3.13 meter gives a maximum bending moment at mid span equal to mu WL square by 8. So putting all the values, that is this 11.81 total UDL multiplied by 3.13 square by 8 comes 14.46 kilonewton meter. Now we convert this in Newton millimeter, comes 14.46 in 10 to the power 6 Newton millimeter. Now for this bending moment, one step is to check the depth in flexure. We'll check that depth in flexure in different lecture. So the basic step after this comes, for this bending moment, how to calculate the main steel area. So the next step is calculation of main steel AST. So as per IS code and SP16 page 48 table 2, the one criteria is to design the main steel based on mu by BD square ratio. So mu by BD square ratio comes 14.46 into 10 to the power 6 divided by B 1000 into D square, that is 130 square, and it comes 0.855. Now for this ratio from the SP16 table 2, we get PT equal to, that is for the value available for in the table is between 0.85 and 0.9. So we have to, the value corresponding to 0.85 is 0.248 and values corresponding to the next higher value 0.9 is 0.264. So we have to interpolate between these two values, and by interpolation we get PT equal to 0.2496%. So from this percentage we get the area of steel AST PT by 100 into BD, that comes 0.2496 by 100 into width of the slab 1000 millimeter into a small d 130. So total area of the main steel comes 324 millimeter square. So this is the main steel which is taking the entire tensile stresses. So now next important steel for this one-way slab is, that is the calculation for distribution steel. Distribution steel is designed as per IS-456 page 48 clause number 26.5.2.1. Now according to this clause we get the minimum reinforcement in a steel, minimum reinforcement area in a slab. So for Fe415 steel grade, the minimum steel area in slab is recommended by the code is 0.12% of total cross section of slab. So 0.12 by 100 into 1000 B into total depth 155. So it comes 186 millimeters square. So we have now designed the area of distribution steel as well. Now the most important next step is to select the diameter and spacing of bars. So for this we can refer to the ISP16 also. One ready-made table is there to select the diameter of bar and corresponding spacing, but manually I am just calculating. Suppose the total area of main steel is 324 millimeters square as we have obtained. If we use 10 mm diameter bar for main steel, so its one bar cross section is 78.5 millimeters square. So center to center spacing for this main steel comes 1 bar area 78.5 multiplied by the 1000 mm for which we have designed width of the slab, divided by total AST which we have obtained 324. So from this formula we get 242 millimeters center to center spacing of the main steel bars. Now for this data, we can provide the main steel 10 mm diameter bar at the rate of 242 millimeters center to center. Now similarly for distribution steel, the area which we obtained is 186 millimeters square. If we provide 8 mm diameter bar for distribution, then 1 bar cross section area for this 8 mm is 50.24 millimeters square. So cross section, the center to center spacing of distribution steel in this case would be 50.24 multiplied by 1000 divided by 186. So this is 270 mm center to center. So we can provide the distribution bar as 8 mm diameter bar at the rate of 270 center to center. So this way we have got the area of main steel and the distribution steel. The next, another important step for the one-way slab design is to check the slab for cracking. So as per IS 456 page 46 clause number 26.3.3, the cracking suggests what should be the maximum spacing between the bars. So for main steel, the spacing between bars can be either 3D, that is 3 into 133 90 mm, or 300 millimeter, that is the maximum value suggested by IS code, or the 242 millimeter which we have calculated. So allowable spacing would be the minimum of these three, least value of the above, that is 242 millimeters center to center. Again, for the minimum space, maximum spacing allowed for distribution steel, for this the guideline says first option is 5D, that is 5 into a small d 130 650 millimeter. Second option is 450 millimeter maximum value, and the third option is the 270 mm, that is the design value which we have calculated. So allowable spacing of the distribution steel bars would be 270 millimeter center to center. So this way we have calculated the spacing between the main bar as well as the distribution bar. Now the most important step of the one-way slab design is to draw a reinforcement sketch. So I have just tried to draw a reinforcement sketch for the total slab dimension out to out is 3 meter plus 300 plus 300, that is 3.6 meter, and the length of the slab out to out, that is 9 meter plus 300 plus 300 9.6 meter. So we have the out to out area of the slab. In this slab, suppose for providing the main steel. Now main steel area is generally provided in the bottom of the slab, that is bottom steel is nearer to the tension phase, that is the bottom phase is the main steel. So main steel is having a top bars, it is bent up at the support and it goes to the top of the support. So near the supports, 50% of the steel goes on the top surface. So how we can provide this in actual construction? We take this first steel bar, suppose, from the right side and right and top of the right support, and goes to the nearer to the left support up to a distance of L/7 from the support. So L/7 length we have taken. Up to this it is coming straight from right, then it is bent up and goes to the top of the left support. Similarly, the next bar would start from the left support and goes up to the L/7 length of the right support, and it would then be bent up and goes to the top of the support. So this way we have arranged the total number of bars in this way over the length of 9.6 meter, excluding the cover. That is, the cover from this would be 20 millimeter, this side 20 millimeter, this side 20 millimeter, and that side also 20 millimeter. So deducting the covered area, we have a bent up schedule of the main bar, that is, it will having a straight length of 2852 mm, and then it will bent up and at a top length of 708 millimeter. So this side a 20 mm cover is left, and this side also a 20 mm cover is left. So a bent up is for a height of 100 millimeter, 115 millimeter basically, because 20 cover on top, 20 cover on bottom. So from 155 total depth we deduct 20 and minus 20, so we get 115. So this way we have a bar cutting length, bar bending schedule, a straight length of this, and then a bent up length of 708. So number of bars, if you calculate, the total length is 9600 minus cover from both end 40, divided by the spacing of the bar, main bar 10, 5, 2, 42 center to center plus 1. So we get a total approximate 41 number of bars, and this way we can arrange. And when we draw a cross section at x6, then this bar, main bar is shown here, the bottom bar, straight bar, and after a length of L/7 from this support, it is bent up. This side also it is L/7, it is bent up. Next, for the distribution bar, there is no bent up in distribution bar. It is provided on the top of the main bar, just like see, if you see, these are the main steel. On the top of this is the straight distribution bar, and these knots we see in the bars are tied. Both the main steel and the distribution bars are tied at every junction. So these circles, black circles, denotes the distribution bars. So it is on the top of the bottom bars, and it is below the top bars, because the function of the distribution steel is to keep the main steel at the proper position, as well as to resist the all temperature and shrinkage stresses developed in the slab during casting and curing. So both the type of steel are important. So if we calculate the bent up total of the distribution bar, then its number comes, total length of the bar is from the central area 2144. For 2144 divided by the spacing of the distribution bar, 270 plus 1, 9 bars. So from here to here in the central zone, middle area, only 9 bars are required. And then for the top bent up area, in this area and this area, so 4 bars are required in this area. 708 divided by 270 plus 1, that is 4 on top, that is the 4 on top and 4 on bottom. So total 8 bars. So 8 bars would be required on the left and the right support area, and 8 bars on the left support area. So the total number of bars required would be 9 plus 16, 25. So this way, it has been tried to clarify the reinforcement sketch of the one-way slab in the plan as well as in a cross section, how it is arranged, how it looks, and what are the main points which is to be taken care during the time of construction. So this way, thank you very much.